that is A, multiplied by the vector A with all the components, in this case A0 and A1. So now maybe it is also easier to get the meaning of A. So the rows of A, this is A, this is the matrix A. The rows of A are X evaluated at correct node locations. And in fact, you have X1. So in this row, you have X1. And in this row, you have X2, that are the node locations. If you make also the product, the match product, you will also see that the node 2, so the row 2 is the node location for the for phi2, right? Then from this, we can also invert it so that we can evaluate A as the inverse of A multiplied by the vector phi with our solution evaluated at nodes. And now, if we substitute the definition of phi here, this one, in this new equation that we have, we have phi is equal to x multiplied by the inverse of A multiplied by the vector of the nodal values. So now, actually, as you can see, we have a direct relation between the field phi and the solutions got from the nodes. So this means that actually what we have here, so the product by the row vector X and the matrix and then the inverse of the matrix A is actually what we call N, that are exactly our, is the definition of our shape function. Is a function that is described, again, what I said before, it is describing how the nodal values can be interpolated through the shape function to give a description of the entire scalar field. Okay? So this is, of course, what happens inside the element between two nodes, but it does not guarantee what happens at the interface. So if you are going from an element to another, what happens? You have a smooth interpolation of what you have between one node and the other. Then maybe you have a sort of, there's a not smooth continuation of the distribution of the field, because the shape function are only acting between nodes. I don't know if you got this point. So it's just a way to have the capability to understand what happens from one node to another. But then when you go from the immediate left side to the immediate right side of a node, you may have a discontinuity there, because the shape function is not taking care about the transition between one side of the node and the other side of the node. Okay? So in that case, we have to deal with the continuity. Do you have any question about shape functions before I go ahead? We will go back to this for the rest of the today lesson, but if you already have any questions, just tell me.
Professor, I have 2 questions.
Yes, there are a question from Teams.
So my first question is, a row vector is just a matrix with just one node, right?
Yeah, correct. So it's
Okay.
yeah, correct.
And then my second question is with the shape function. So it's only what's happening within the material. So like the piece we were just looking at, where it's just that one piece, but we don't know anything about the edges or the behavior at the, like you said, at the interface of the material. It's just what's happening on the inside.
Well, okay. So the first question was about what is a row vector, and the answer is actually is a matrix with only one line. So it's just one single row, it's one line. The second question is about if I got correctly, the limitation of the shape function. So what happens, I mean, what is the interface we are dealing with, right?
So I was just wondering, the shape function is only about the bulk of the material, but not the exterior surface.
Well, it is not a matter of the inside or the outside part of the material, but it is how, I mean, the shape function is only a mathematical interpolation of the values, the result that you got from two nodes, or at least within one element. Actually, we only saw examples with elements with two nodes, but whatever is the number of nodes, the shape functions are taking care about what happens in one single element. So whatever is outside the element is not taken into account for the interpolation procedure of the shape function. So it doesn't matter if you are considering an element inside the material at the interface or maybe at the boundary condition. The idea is that from the result that you got from the nodes, you are able to understand what is the distribution of the field within the element. Okay?
Okay, thank you.
Okay. Okay, so what happens is that outside the element? Well, let's start with some definitions. So it is a matter of continuity. I anticipated. So we can define CM continuity to define to describe the transition between two elements. If the transition, let me make a couple of examples. So this is a generic field phi, and in this case we have two elements, so three nodes and two elements, element 1 and element 2. And then let's see, okay, let's start with this. Let's take two examples. One is about a field that we already found to be like this. This should be a square and like this. Okay, so we found the nodal values in 1, in 2, and 3. We use linear shape functions to relate what happens in between the nodes. So we found this distribution and this distribution, but we don't know what happens in terms of continuity between, in the transition between element 1 and element 2. Okay, so this is the case we can call phi1. Another example could be to have something like, this is much more complex, something like this. Where we have, again, this is the distribution of another field, where we have, for example, a quadratic interpolation here and a linear interpolation here. Again, we have the nodes, the nodal values, and we can interpolate with functions. But the difference between phi1 and phi2 is in their first derivative. if we trace the first derivative of these two fields, again we have node 1, node 2, node 3. For the first, we have, since they are linear shape functions, we have something like this, right? So linear functions, we have constants once you have the first derivative. For the second one, instead, you have something like this. Because you have, considering it as a, let's say, its first derivative as a sort of ramp, and then it is going to be constant for the between these two. That in the first case, phi1 has a first derivative that is, it has a discontinuity. There is a sort of singularity here. In the second case, phi2 has a first derivative that is